Hello, and welcome to today's WJE webinar, Adhered Veneered Wall Systems, Where to Start to Achieve Better Results. I am Liz Pimper, and I will be your moderator. During the next hour, architects Renae, Kwon, and Daren Kneezel, and engineer Leah Ruther will draw on WJE's extensive experience investigating failures for design and construction, and will present general strategies to achieve a successful adhered veneer installation. This presentation is copyrighted by Wisjani Elsner Associates, and now I will turn it over to Renae to get us started. Renae?
All right, thanks, Liz. So we'll start off with our learning objectives here. So by the end of the presentation, we want to make sure that you're able to contrast prescriptive design requirements versus engineered design requirements. And we're primarily going to focus on prescriptive design requirements, but do realize that there is the option for engineered design as well. Explain industry guides and standards such as ASTM and ANSI and how they relate to adhered veneer products and also installation. And then identify at least 3 of the most common failure mechanisms for adhered veneer systems. We get involved in a lot of failure investigations, so a lot of the knowledge that we have of adhered veneer systems comes from those investigations. And then finally, summarize key quality control steps to be considered during construction that can lead to a successful installation. So taking a look at just kind of the general outline of where we're going to go today with the webinar, I'll start off with the what and the where, or the what and the why of adhered veneers, and then Leah's going to get into code standards and guidance. And then Daren's going to touch on some case studies where things went wrong. And then finally, we'll use a few case studies to illustrate design through construction, a road to success. So starting off with adhered veneer basics, this is a very generic kind of wall system, typically something we've seen maybe 10, 15 years ago. But this will give us an idea of the different components that we see in adhered veneer systems. So starting up with our backup, this may be a wood stud or steel stud backup. It could even be a concrete masonry backup. Then outboard of that, we have our water resistive barrier. Historically, a lot of times we saw 2 layers of building paper was very common. Then outboard of that, in this example, we're using our backup as a stucco substrate, and this consists of a mortar scratch coat with an embedded metal lath. And that metal lath is going to be mechanically attached to our backup. Then outboard of that, we have our adhesive mortar setting bed, sometimes referred to as our adhesive mortar, sometimes called the setting bed. There's different language that's used to describe this component. But essentially, this material is going to be used to adhere our veneer units to our backup system. Then the joints between the units can either be pointed or they can be left open in a dry stack application. And here's just kind of a quick image looking at some of these different components. So the bottom left, we can see that lath that we were talking about that's mechanically attached back to the backup, and the building paper behind that. There's also a fluid applied air and water barrier is the black material on the right-hand side, as well as a drainage mat is the yellow material. So over the years, as these systems have evolved, there's been additional components that are added into these, and we'll go through a list of a few of these. So continuous insulation, due to our changes in the energy code, a lot of our adhered veneer systems are going to require to have continuous insulation. So in this example from IMI, the image on the bottom here, the rigid insulation would be the blue element that we see. Drainage mats are also another common element that is being included in our adhered veneer systems. The top image here shows one way that a drainage mat could be incorporated into an adhered veneer. So with this system here, we have our scratch coat. You can see the top of the lath is exposed, and that's adhered to some furring. The furring elements are going to be these vertical elements coming down the wall, and that provides a space so that our stucco has a cavity behind it. And the black material is the drainage mat that is inboard of that stucco backup. We also have different types of cement board backups, or different types of backup, one of them being the cement board. Sometimes we'll see this with the use of continuous insulation because we have that continuous insulation that's inboard, and then we need another backup system and cement board can function as that backup for attaching our adhesive system. Polymer modified mortars are becoming more popular in the marketplace for sure. We see these because they have increased bond strength, and Leah will get into some of the code requirements and where the code is moving relative to polymer modified mortars. Panelized systems are also something that we're seeing now. This may be, for example, thin brick that is included on several thin brick pieces that are included on a panel, and then that panel gets adhered to the system. Large format tiles, this is any tile that is over 360 square inches in size. And at that point, you move to an engineering design. But some of the issues we've seen with large format tiles, because of their size, they can be challenging to install properly, and making sure that all the ridges on the adhesive mortar are fully collapsed. And when I say ridges, we're talking about the adhesive mortar when it's trawled onto the backside of these large format tiles, and then it's placed onto the wall and worked into place. We want to make sure that all those ridges are collapsed and there's full contact between that adhesive mortar and the backup. And then just the different veneer options that are available now, like glass tile, ceramic, porcelain tile. We've even seen honeycomb back stone that is in an adhered application in interior applications. So what's the appeal with these systems? We're seeing them more and more on the marketplace. They can be lighter system. We require less structure to support them. In retrofit applications, we may be using these to change the appearance of an existing wall. The example photograph here is a precast where we're using thin brick to change the appearance of this exterior facade. Aesthetics may be another reason. There's a variety of different materials that can be used in an adhered application. Value engineering, these systems can be cheaper than maybe our traditional brick masonry cavity wall construction. There's a perception of easier installation. Maybe there's, we say that perception because we're gonna go through some of the challenges with installation, but there's this perception that maybe you need less skilled workers to install these systems. There's proprietary designs out there, so you basically select, one manufacturer and can provide the entire exterior wall system. And then schedule, decreasing the time for schedule may be another factor influencing this. So what's the difference? These adhered masonry claddings are generally intended to look like our traditional brick masonry cavity wall or a stone wall. But there's multiple design considerations that are different from our traditional wall systems that need to be considered, such as movement joints or bond strength of our adhesive mortar. Also, the water management between the different types of systems is going to be different. So with our adhered veneer claddings, we're more relying on either a barrier system or a water managed system. A barrier system being that we're preventing that water from entering the wall system, whereas a water managed system is we accept that some water is going to enter our wall system, but we have a means for managing that water. These systems are going to be heavily dependent on installation. From our experience, the majority of the distress and failures that we investigate a lot of times are related to something to deal with installation. Now, that's not to say that there aren't also issues with design. We've also seen design problems, particularly maybe when you have a complicated project, or maybe there just isn't enough information in the design documents for the contractor to properly install that system. There's limited redundancy in the attachment of this system. Once we have adhesive bond failure, we can have failure of the units where they fall off the wall. And when we do have distress of this nature, it tends to be systemic. We'll have potentially leading to large scale repairs or even reclad. And when we do have reclads, a lot of times you have to go back with the same system because, again, that structure wasn't designed for a lighter weight type of cladding. Maintenance can also be challenging. Repointing a thin brick is going to be very different than repointing your traditional cavity wall system. Aesthetics can also be challenging. Problems with efflorescence is shown in the bottom photograph here. Also, just making sure that the flatness of our substrate is there, because again, since we're adhering these veneers to that substrate, if we have waviness or we don't have a straight corner, that's going to be seen in the final application. And then finally, just regional differences to consider, such as freeze thaw, seismic, even temperature extremes. But that's not to say it's all doom and gloom and we shouldn't be using these systems. Here's a few examples of adhered veneer systems that have been in place for over 50 years. On the left-hand side, this is a building in a freeze thaw climate. It has an adhered tile on it. And we were out here for a routine inspection and had to take off a couple of tile. And I was really surprised by how well bonded the tile was to the substrate. On the image on the right-hand side, this is a building in the Southwest, so kind of a dry, hot climate. And this is a 2.5-inch thick glazed brick that's adhered to a reinforced 2-inch thick concrete substrate, somewhat like a scratch coat. And there's no horizontal expansion joints in this building, and it's doing amazingly well. There's very limited distress on it. So here are just a couple examples of these systems that are functioning very well. And next, I'll hand it over to Leah to get into codes, standards, and guidelines.
Thanks, Renae, and thanks for sort of setting the stage for us today. So I'll be looking to provide just an overview of codes and standards as they relate to adhered veneers. So what you see on the screen here is kind of a flow chart that represents various paths to code compliance. Naturally, we start with the International Building Code, in this case, the 2024 version. By reference, that incorporates the TMS code, so TMS 402 and 602. That's broken into two sections. The 402 is the building code requirement for masonry structures, and the 602 is specification for masonry structures. Again, by reference, that incorporates various ASTM standards and ANSI standards. You'll also note direct links from the IBC to the ASTM standards, as well as the IBC to manufacturer instructions. There are several other industry guidelines that provide some guidance on design and installation that may not be incorporated directly to these code references or codes, but can be valuable for when considering these systems. One thing I want to point out is the TMS provides a prescriptive method, an engineered method, and Renae touched on that briefly, but just for general understanding, a prescriptive design is a code-based approach where you follow predefined rules, limits, and details in the code. If you stay within those boundaries, then there's no project-specific engineering analysis required. It's usually a simpler and faster approach, but it does limit you to specific conditions, and we'll kind of get through some of those. You can imagine then the alternative to that is an engineered system or engineered design, and that's a performance-based approach that uses engineering analysis and calculations to show that a system meets the design code intent, and even if it falls outside those prescriptive limits. So this offers some more flexibility, but does require an engineer's judgment and documentation for compliance. So what you see on the screen here is just a list of references that are incorporated into that prior flow chart, as well as guide the content included in the following slides. Not going to read through all of these, but just providing them here for reference. So to set the stage, I know Renae went through some of these different elements of a traditional wall assembly, but extracted this wall section from the TMS code, and it just represents a traditional assembly that incorporates an adhered veneer system. So I've broken it out into 3 categories. You've got your thick set system, which includes a metal lath, a scratch coat, and a setting bed. There is a thin set system available, and that's when you can eliminate the lath and the scratch coat. It's often not required when adhering these units or veneers directly to concrete, unglazed clay, or concrete masonry, or cement bakery units. Then you have your veneer, which Renae touched on, can be brick, stone, tile, and a number of variations within that. And then not to rule out all the other components, the insulation, water-resistant barrier, drainage mat, cement board, and various backup wall systems. Obviously, that leads to many, many combinations and systems available and can make code compliance a little complex. So I'm not going to dive into all the code requirements for all the things listed on the screen, but just going to focus in on these 4 elements: the lath, the scratch coat, setting bed, and the veneer, and what does code say about these 4 particular items. And again, focusing on the prescriptive requirements for that, and then understanding when you move outside of those, you're in the engineered system or design requirements. To start us off, we'll have the metal lath. And so the requirements here are listed on the left-hand side. And then on the right-hand side, I have some commentary. And this is meant to sort of provide background and explain the why to these requirements so that they come to life a little bit more. So for metal lath, kind of an obvious one is corrosion-resistant material. Obviously, these are in exterior environments, and so that reduces the susceptibility to corrosion. Fully encapsulated lath and scratch coat is really important, and we've seen a few failures because we didn't fully encapsulate that lath, and we start to see corrosion of the lath itself. In the TMS code, it does provide some fastening requirements in some prescriptive tables, and those are predominantly based on the weight of the veneer system as well as the cavity width. And the cavity width is defined as the distance from the outside face of the structural backup, not including the sheathing, to the backside of the scratch coat. One distinction there is that those tables are only for wood and metal studs. So if you're going to use any type of girt assembly, then the fastening requirements need to be engineered. There's also a requirement that the lath be furred, so a 1/4 inch furring. This does promote that encapsulation of the lath, and again, kind of reduces that susceptibility to corrosion. You can consider self-furring lath or other furring methods. And there's also some guidance regarding the different types of lath and various weight limits or requirements on size in different ASTM standards. So just a couple of good examples of lath failures where that didn't really adhere to these requirements. So on the left-hand side, you can see that the lath is actually starting to detach from the wall, kind of leading to a structural failure. And then the image on the right is where, again, we didn't have full encapsulation of that lath within the scratch coat. And so you're starting to see corrosion and leading to that beginnings of a structural failure of the system. Moving on to mortar scratch coat. So there's a minimum thickness there. I know I sound like a broken record, but that does help promote that full encapsulation of the lath. And then there's a horizontal scoring requirement, and that promotes mechanical bond between the scratch coat and the setting bed. And one thing to keep in mind when scoring that scratch coat, we want to be careful we're not incidentally reducing the thickness below that 1/2 inch requirement, because you may incidentally expose the lath. And the image on the right is a good example of when that occurred, and you can start to see some corrosion of that lath happening there. Just want to pause and just highlight the reference here. So all of these requirements listed on the screen do come from those list of references that I showed on a prior slide. Just to bring it to life, so here's the 2 requirements in the 2024 IBC regarding the thickness and the scoring of the lath. So moving into some additional guidance regarding scratch coat, you can see there's a reference here to the ASTM standard 1780, and that recommends a 48-hour cure. And that's intended to ensure this firm surface. And the purpose of that is to resist any force of pressing units into place that might unintentionally move the lath or reduce that thickness. So that's just a general recommendation there. And then along with that is dampening the surface with water prior to placement of the unit. Same thing, that eliminates potential for moisture absorption or kind of wicking the moisture out of the setting bed. So moving into mortar setting bed, 3/8 inch nominal thickness is a requirement for the setting bed. Again, that promotes full coverage and mechanical bond to the scratch coat. The next 3 items kind of go hand in hand, and that's full setting bed and working these units into the setting bed and mortar squeeze out. So full setting bed means the entire backside of that unit should have full coverage of mortar. This promotes bond and then goes into working the unit into setting bed, ensures full contact. So what we're really trying to eliminate is potential for voids behind the units that can reduce the bond strength and also may reduce potential for freeze-thaw damage. You can imagine if you're in a freeze-thaw environment and you have voids behind your unit, if you get water in there, we've seen it where it starts to actually pop some of these units off of the backup. And so I think the TMS has a nice description here. It suggests to install the veneer unit, filling the space between the veneer unit and the backing with mortar, use sufficient setting bed mortar and installation pressure to create a slight excess of mortar to be forced out between the edges of the veneer units. That's that mortar squeeze out. So you want to see a nice squeeze out around your unit. Regarding the mortar type, so this is something Renae mentioned, is polymer modified mortars are required in the 2024 IBC as well as the 2022 TMS code. This is a difference from the 2016 IBC, which allowed the type S. Obviously, it does promote that superior bond strength, but something to keep in mind when considering design of these systems as we move into adopting those new codes. Regarding the veneer, so there's some prescriptive limits on the average unit thickness as well as the unit weight, so 30 pounds per square foot. I want to focus in on the unit area. So the TMS provides some clarity on or expectation on the unit area. And so it says that the bonded surface area of each adhered unit shall not exceed 720 square inches. And then units that have a bonded surface area greater than 360 square inches are required to have a installation procedure approved by a licensed design professional. And so really the limitations there are imposed to reduce difficulties of handling units and installing large units to ensure we get a good bond. Units greater than 360 square inches can be more susceptible to those challenges to getting proper bond. And so consideration should be given to back buttering them and or using multiple workers for installing those units. And just for clarity, 360 square inches, a unit size of 20 inches by 18 inches, it represents that area. Another requirement here is the minimum shear bond strength, and that's set at 50 PSI. And that qualifies that an adhered unit develops adequate bond strength at its surface with a specified adhesive over a specified substrate. And I think Daren touches on this in a couple of his case studies. So moving into just some general requirements, there's some limitations on the overall assembly thickness. So making sure that that's 4 5/8 inches or less. The total assembly weight is limited to 50 pounds per square feet. Maximum height is 60 feet. Recommends only vertical application, so no soffits or similar applications. And again, those are the prescriptive limits. If you move outside of those, you're into the engineered system. There are some limitations on deflection, just obviously to limit veneer cracking. And then I want to highlight some movement joint placement. So I have a whole slide dedicated to that. So the Brick Industry Association puts out a tech note that's really helpful when guiding designers and installers on the spacing between movement joints. And it recommends no more than 18 feet in both directions, and then also not exceeding 144 square feet. Traditional systems, so traditional veneer or brick veneer is usually between 20 and 30 feet. So this is a little bit tighter. And we have seen some failures related to inadequate spacing or, and then also kind of related to those last two bullets, which suggest that the veneer, you need to have a joint extend through the entire thickness of that adhered veneer system. So your lath can't cross over that joint. And then also we need to make sure we're aligning those joints with the substrate. So on figure 7, you can see that the CMU has a movement or a control joint that's aligned with a joint in the adhered veneer. So some key elements regarding movement joints, and I think Daren has a good example or case study that where we saw a failure regarding these, so makes for a good segue to hand it off to him.
Okay, thank you, Leah. So being a company that specializes in forensic investigations, we're able to observe the mechanisms that commonly result in the failure of adhered veneers. And a lot of these are just not following code, not following industry standard practices. So I'm going to go through several case studies here. First of all, a case study on systemic adhesive failure, then one where we saw the metal lath failure, then insufficient movement accommodation, and finally wrapping up with a bunch of other potential failure modes that you can see. So on this first case study where we saw systemic adhesive failure, this had been in service for approximately 2 years in a freeze-thaw environment. So it's on a 3-story building, and we saw approximately 30 units disengaged after those first 2 years in service. The system here included 1-inch thick manufactured stone veneer, a polymer modified thin set mortar at the plane indicated by that arrow, that you're actually seeing sealant there because it was an inspection opening, but there's mortar at that plane. A fluid applied air and moisture barrier over cement board backup. And then at the perimeter of these, there was no joint material, no sealant or mortar, and so it was a dry stack system. We went out and sounded several units with a rubber mallet, and we found that throughout the facade, there was up to approximately 50% of the panels made a distinct hollow sound indicating lack of adhesive bond. We found many units at those hollow areas where they could be removed by hand. And in the right photo, you can see there the mortar ridges, as Renae was talking about, they're uncollapsed. You didn't get good squeeze out around the perimeter of the unit and didn't get good contact at the backup. The left photo here shows another area where the unit could be removed readily by hand, had minimal adhesive contact with the backup. The red shading shows the small portions of the unit that did have some amount of adhesive contact with the backup. This all indicates insufficient pressure was applied and you didn't get the good squeeze out on the perimeter. The consequences of that are you clearly have reduced adhesive capacity because you've just got a smaller area where it is adhered. There's open joints in the system because it's a dry stack that allow water into the backup, and then that water can freely travel laterally within the backup, deteriorate the adhesive bond. And in a freeze-thaw climate like this, it can lens, so you get ice lensing where it forms subsequent layers of ice and eventually can push out on the units as well. In this case, the veneer manufacturer actually required within their written manufacturer's instructions that they achieve the squeeze out on the unit perimeters as well as a fully pointed system, so it did not permit for a dry stack system as was installed. So typically on most projects, we're looking for a way to salvage the facade or identify a repair strategy. But unfortunately, in this case, because the units don't have a reliable bond, it was widespread. There was really no practical method to address the existing distress conditions without just removing and replacing the entire adhered veneer. So that was our recommendation. On top of that, installing a new adhered veneer, we recommended several quality control measures, including mock-ups, testing, confirming adhesive coverage, all of those sorts of things. They're included in a lot of the industry guides, and Renae is going to dive a little bit deeper onto those in a bit. So our takeaway on this, of course, important to follow manufacturer's instructions and code and get that mortar squeeze out the perimeter, and all of that would have mitigated the water that gets to the backup and deteriorates the adhesive bond. Now, a second case study, this one's on metal lath failure. So in this particular project, we saw widespread delamination of veneer units on a two-story building in a freeze-thaw environment. There were initial reports that individual units had failed and debonded after about 5 years in service, but at 10 years in service at the time of our investigation, these units were coming off in sheets. The system here includes a 1-inch thick adhered bluestone veneer, adhesive mortar, mortar scratch coat with that's encapsulates what was specified to be a self-furring galvanized metal lath to allow that mortar, the scratch coat mortar, to fully encapsulate it, a weather barrier, and all of this over plywood sheathing and metal stud backup. Some of our field observations here, we saw widespread buckling of units, outward displaced units throughout the facade as shown on the left, and then occasional poorly adhered individual units as shown on the right. We also saw widespread efflorescence, which is the white colored deposit indicated by the arrows. That basically occurs when water can enter between the joints, get into the backup mortar, strip this water-soluble components out of the cementitious materials in that mortar, evaporate, transport those materials back to the surface, and leave behind a salty white-colored residue. We also performed sounding throughout this facade, and one interesting note here, it was widespread hollow sounding indicative of delamination or poor adhesive bond, but it was a little bit less on the east and north elevations, still widespread, but less on those two elevations relative to the south and west elevations. When we started making inspection openings, we did find that the lath was not self-burred, so it was actually didn't have good coverage on the back surface with the mortar scratch coat. However, you can see in the orange arrow there where you had good adhesive mortar outboard the lath, the lath was actually still in good shape on this project. But where there was limited or missing adhesive mortar, you can see with the yellow arrow there, that corresponded to areas where the lath was corroded. And the corroded lath was readily torn by hand and really didn't have any engagement or attachment to the backup because the attachment couldn't secure to the lath. We also did some inspection openings and testing at hollow versus solid areas on the facade, and we found a good correlation between the amount of contact area and whether or not it was hollow or solid, as well as we did some testing and the applied stress was greater at the solid sounding. We also had the opportunity to bring several samples back to our in-house laboratory in Northbrook. The right photo here shows a cross-section of the metal lath. On the right side of that, the red arrows point to galvanizing on that lath, and this was intact lath, so in good shape, not corroded, and you can see galvanizing on the right side. But on the left side, where the orange arrow, it shows a lack of galvanizing on that surface. We also measured the weight of the lath and found that it did not meet the specified requirements. Another thing that we saw in our laboratory evaluation was that the depth of carbonation varied by exposure. So it starts explaining why you have more distress on the south and west elevations relative to the north and east. The north and east actually had less carbonation. And what that means is basically there's a chemical reaction that's occurred in the cement. It lowers the pH of the mortar and it reduces the protection of the metal lath. So greater carbonation is the greater potential for corrosion of the lath. So after doing our inspection, we concluded the primary causes of the distress were a lack of adhesive mortar contact that resulted in corrosion and detachment of the metal lath at those locations, as well as the moisture being able to get back there and deteriorate the adhesive bond, similar to the first case study. Secondary causes were that the metal lath galvanizing and weight were insufficient or less than specified. And there was the explanation for kind of the patterns we were seeing was that there was differences in mortar carbonation. So as with the first case study, our recommendation was to remove and replace the entire adhered veneer because it was, again, widespread distress. And the takeaway, very similar to the first, adhesive contact is critical in an adhered veneer. Water can get back to the backup, deteriorate the bond, but also the various components that attach the whole system to the backup. In this case, that resulted in more widespread delaminations. Now getting into a third case study, this one's about insufficient movement accommodation. So this one differs from the first two case studies because this one's not in a freeze-thaw environment. It's in a hot and humid environment with mild winters. And we actually have two different portions of the building with experiencing different types of failures. So on the base portion of the building, shown on the left, we saw large areas of brick tile veneer that delaminated. And then on the right, it showed there's about a 20-story, slightly over 20-story tower that had adhered brick veneer, and there was local displacement at floor lines within the adhered veneer. So the system at each of these, on the left is the base building as a 9/16 inch thick individual brick tile units. with a mortar bond coat, mortar scratch coat. All of this adhered directly to a CMU backup. And on the right, the tower, same brick tile units, had mortar bond coat and a metal or a scratch coat with metal lath, all attached with to the backup stud framing, and it has a weather-resistant barrier there. And this was a concrete framed building. So at the base building, some of our observations were bulged brick tile veneer, particularly where there are long horizontal expanses of brick, no movement joints at those locations. And in general, where there were windows or louvers interrupting that long horizontal expanse, there wasn't the same sort of bulging. At the tower, we saw that the buckled units at the horizontal were aligned with horizontal movement joints in the brick tile veneer. And when we made an inspection opening or several inspection openings at the backup, we saw that the plastic control joints at the backup scratch coat are compressed. So those are shown, the bulged brick tile as well as compressed mortar there in the left and the compressed control joint on the right. We also did some limited shear bond testing just to see how well it was bonded away from the areas that exhibited distress. So this shows the results at the tower, and we saw that the bond strength was about close to 100 psi, so still quite well bonded away from the existing distress. So some conclusions as far as the base building, where there's a lack of movement joints in combination with long expanses of brick veneer that were constrained between projecting piers, you get compressive stresses that accumulate within the veneer as the veneer wants to expand. The veneer has no place to go because it is constrained by those piers, so it buckles outward, and that can only occur after the bond strength has been overcome, where the buckling stresses overcome the bond strength to the backup. At the tower, the mechanisms were concrete frame shortening, so the concrete frame shortens over time, the brick veneer expands, and that results in vertical compressive stresses within the veneer. And then on top of that, we noted that the movement joint at the backup did not align with the movement joint at the brick, so this creates a hinge at that location that's prone to buckling. So in this one, slightly different from the prior, we didn't need the comprehensive reinstallation of the adhered veneer. In this case, we could just locally remove where the mechanisms were at place. So where there was insufficient movement joint, the long expanses at the base of the building, and then just locally where the brick had buckled outward, because away from there, we had good bond strength. So overall takeaway on this one, movement accommodation is critical in an adhered exterior veneer just to accommodate the variable movement of materials. And on top of that, alignment of the movement accommodations between the veneer and the backup is also important in practice. So going through a list of some other potential failure modes, just briefly, one is the facing material itself, making sure that it is suitable for the intended application, whether it's freeze-thaw climate or whatever, just making sure it's appropriate. That can result in spalling distress, aesthetic distress, but also affect the bond at the backup if that distress occurs at the back surface. Dust and debris at the interface that can interfere with bonds, so dust in the environment due to other operations, just being careful about that. Mortar skinning over, so allowing the mortar to cure too long before installing the unit so you don't get adhesive bond and you don't get that squeeze out. Insufficient mortar or insufficient pressure to achieve the squeeze out and still having uncollapsed mortar trowel ridges. As Renae mentioned, large tile mortar contact, we've seen where it's difficult to achieve good contact on those larger tiles just because of the inability to get as uniform of pressure on it. So you can see on this photo, you've got kind of the back buttered material on the left with the trowel ridges still showing, and then the material on the backup that still troweled, and neither of the two contacted each other or collapsed those ridges. Now there are ways to achieve better contact, and there are mortars that are specially formulated to help with that, and trowels, but it's something to watch out for on larger tiles. And then reflective cracking. So if you've got the facing material bonded directly to the backup, then there's the potential that if the backup's an unstable material, the cracking that occurs at the backup can reflect to the surface. And with that, I'll hand it over to Renae to talk about successful installations.
Yeah, so as Daren went through some of the things that can go wrong with these installations, now we'll kind of outline a path for success. So our roadmap for this is going to be, attention through design all the way through construction. So in design documents, we're going to want to make sure that we have comprehensive drawings and specifications. We're including code compliance and industry guidelines. Other considerations that may be included during design may include laboratory testing, pre-design testing, history of in-service of similar projects, similar climates, so kind of that history of use. Also consideration for requiring qualified installers. Project mock-ups, we'll get into those, but this, in my opinion, is one of the most important steps to a successful project, is having those pre-construction mock-ups, and then during construction, making sure we have oversight and quality control. So digging a little bit deeper into construction documents, some things we should consider to include in our drawings and specifications. And this list is not exhaustive by any means, but it's kind of some of the highlights that we wanted to highlight. So water management, thinking about, are we going to have a barrier system, or is it going to be more of a water managed type system? Transition details, making sure we have base of wall flashings properly detailed. We have continuity of the air-water barrier, particularly where maybe we interface with adjacent systems. Movement joints. We had a case study that highlighted what can go wrong with movement joints. So it's going to be important in our drawings to not only provide a detail so the contractor knows exactly how to install that movement joint, but then also lay it out on the elevation so it's very clear where they're intended to be located. And then other components that we have in our exterior wall system, whether that's insulation, drainage mat, how are those getting interfaced between all these elements? We talked about just all of the components that are getting added to our adhered veneer systems. So thinking about how they all come together to provide a system that is that has durability in the long term. Now, with regards to our specifications, we want to include such things as recommendations for our installers, such as certified training programs, adhesive contact requirements. So we want that full mortar bed coverage. And this is also going to limit our moisture collection or migration back behind our adhered veneer stones. We're going to want to define what the substrate deflection limits are. This can be anywhere between, L over 240 to L over 1,000, I think the stone is a recommendation for. So including that deflection limit in our specifications. Outlining our flatness tolerances. So this may be dependent on whether you have a thin or thick setting bed, but just defining what that flatness requirement is for our substrate. Because again, when we're adhering our adhered units to that substrate, we're only as good as that substrate is. And I think it's also important to include what the contractor is supposed to do if the installer gets out there, the flatness is not what they intended. Are they, what is the ramification for that? Include that in your specification. And then pre-construction requirements like the pre-construction mock-up that we discussed, and then quality control measures during construction. Now, during design, there may be some other considerations, and we'll get into some of the elements to evaluate the durability of our facing material. So this is going to be our veneer unit. and then also material compatibility. And what we're talking about here is primarily the adhesive bond between our veneer unit and the backup. So one way to evaluate the durability of our facing material is through physical or mechanical testing. And here are a list relative to different materials, whether cast stone, dimensional stone, of different ASTM standards as they relate to that particular material, defining what some of these physical and mechanical testing standards are. The images here, this is a natural stone, and we're performing compressive strength testing on the left image. And then the other image, we're doing a flexural strength test of dimensional stone. Durability testing is another option. This could include freeze-thaw cycling. So maybe we have a natural stone, we don't have history of its use in the environment and the climate that we're intending to build it in. So durability testing such as freeze-thaw could be used, where we cycle this material through several cycles of freeze-thaw testing, and then again, do physical or mechanical testing on that, even petrographic analysis of that, to see, is this material going to be durable in the long run? Petrographic analysis. This is another tool that we have in our toolbox. This particular example that we're showing on the screen here, we're looking for pyrite inclusions. On the left-hand slide, this is a piece of pyrite within marble. And the reason we're looking for this is that if we do have this inclusion in the stone, it could relate to the corrosion brown staining that we see on the image on the right-hand side here. And then also just the history of successful use. This can be a tool that's used to evaluate the durability of that facing material. So once we have selected our facing material, we also need to evaluate and confirm that there's sufficient bond between the facing material and our backup. One way to do this is through laboratory testing. So ASTM C482 is the laboratory shear bond testing. And with this test, essentially you take your facing material, then you use your adhesive bonding material, whether that's a polymer modified mortar type S. You bond that to a substrate. In the photos on this slide, we have our substrate as a CMU. And then you put a force on the top of that, and that creates a shearing effect. And we're looking to have greater than the 50 PSI shear bond strength that Leah mentioned was the code requirement. Other ways that we can confirm material compatibility may be through International Code Council, ICC reports. So this is where a manufacturer has tested their material and has a prescriptive, like basically an outline of how it needs to be installed to achieve that code requirement, the 50 PSI bond strength. And history of successful use, again, can be used for evaluating the material compatibility. So now moving on to pre-construction, again, we said these mock-ups were really critical. This is going to give us a chance for the installer, hopefully the same installers that'll be working on the project, to install the system. They can, it's their first chance to potentially evaluate all the different components of the system. And then shear bond testing can also be performed in the field. So ASTM C1823 is the standard for shear bond field shear bond testing. And again, this is going to be evaluating the shear bond of the entire system. So that's why it's important to do this testing in the field, because we're evaluating the full system at this point. There's also the possibility for tension bond testing, where a puck may be glued on to the veneer, and then that's pulled in straight tension to evaluate the bonding of the entire system. And another really important consideration during these mock-ups is to review the setting bed coverage as well as the contact. We saw in a number of the case studies where we had failures that some of the issues were coverage or sometimes contact. We may have full coverage of the adhesive mortar, but it's not coming into contact because it's not getting worked in with our backup. Then during construction, we want to also have quality control measures. A couple of options that we have here. The stone ASTM C1242 outlines a measure that is non-destructive, which is kind of nice to use during construction, where you basically randomly pull off a tile or an adhered veneer unit and be able to confirm the backside of that. And that's the image on the left-hand side here. So we've pulled off the tile. We want to make sure, one, that we have full coverage, and then two, that we fully collapse those ridges and we have full contact between our adhesive mortar and the backup. And then some other things to consider during construction could be that shear bond testing, performing some of that, which is shown in the other photograph here, or the tensile bond testing could be an alternative to that. So a few things to kind of wrap up and summarize some key takeaways that we wanted to leave you with. Materials, due to the variety of veneer materials, adhesives, backups, and other components, really the configuration of these systems is almost limitless. So it's going to be the designer's job to consider these various components and how they work together and achieve that desired both aesthetic as well as providing a system that has sufficient performance and durability in the long run. Regarding the code, there's also a variety of code and industry standards that are out there for both design and installation, and really having a good understanding of this to both maximize the performance and then also mitigate failures. And then during construction, one thing that we see is installation issues. So making sure the installer pays careful attention to adhesive contact, which is going to mitigate many of the failures that we talked about and also that have observed in the field. So, and with that, I'll turn it over to Liz to kind of wrap things up.
Thank you, Renee. Thanks, Leah and Daren. Now we will take our first question. For the weather barrier, you talk about paper. What is your recommendation on Tyvek versus building paper?
So I think that sometimes Tyvek is used in lieu of building paper. A lot of that is sort of dependent on the application. We see a lot of residential projects that are maybe using Tyvek. So in that application, I think it makes sense. One thing that I'd like to point out, we have seen failures where, particularly when we're using that stucco substrate and there's lots of penetrations from the lath. I think that's something to consider when we have that multitude of penetrations. Do we still have a continuous water barrier? Do we have to worry about water getting through there? So, but in relation to 2 layers of building paper versus Tyvek, I think if they're installed properly, both can perform well.
I was on mute. Let me try that again. The next question is, should the movement/control joints also go through the setting bed and the lath?
I can jump on that one. Yes, the recommendation is to kind of terminate the lath at the movement joint and make sure that it extends through that full depth of the assembly. The BIA tech note provides some guidance on that.
Okay. Our next question, are there any standard tests for shear bond strength?
Yes, Renae went through some of them. The ASTM C482 is a good one for testing the materials up front in a laboratory. C1823 is a more recent one for allowing shear bond testing in the field to evaluate the bond strength of the material to the backup.
Okay. What are reasonable measures to include in specifications to ensure a quality install?
I think we went through some of those on our point by point on that slide, but I would say, I think we want to make sure that the system that we're installing and some of the issues that we may have with that particular system, we want to make sure that we're addressing that in the specification. So, some of the really important things that I would maybe highlight again, making sure that our installers are certified, paying attention to and requiring and laying out, you know, step by step all the requirements for that pre-construction mock-up is also, I think, really important. I don't know if Daren and Leah, you guys have some other suggestions?
Yeah, that pre-construction mock-up is important for, I'd say, various members of the crew to understand that you need certain requirements. You need to get good adhesive bond, and it's also important to understand the environment that you're going to be in. It's not a code requirement, of course, to do these mock-ups, but it's very helpful and to understand that everything's adhering as expected.
Okay. Daren, since you're already talking, this is a question for you. What is applied stress and how do you test this?
So we basically isolate a portion for the shear bond test, the field shear bond test. We isolate a portion of the facade back to the substrate, about a 6-inch by 6-inch area, and then basically put 2 plates in there that spread apart and apply load to that isolated area. And we just measure the load at which it fails. And then there's 2 different stresses you can back out of that. One is net shear bond strength, which is basically the amount of bond area that you have, what's the strength within that bond area. And then gross is basically the amount of bond strength for the whole area tested. So a 6-inch by 6-inch area, you divide your applied load by your 36 square inch area. So you've got 2 different stresses. The net gives you an understanding of whether your materials used give you sufficient strength. Gross just is more over the area tested.
Okay.
And to add to that, what we're looking for is the net and the growth to be the same, because again, we're looking for that full coverage between the 2. But if we have installations that have voids, then you would be comparing those 2.
Okay. How do you deal with building shrinkage as wood shrinks approximately 1/4 to 3/8 inch per floor?
So I think this is a great question that kind of just highlights the need for a good understanding of our building materials. There can be multiple ways, I think, to deal with that shrinkage, the wood frame shrinkage, but the important thing is to take it into account and not, you know, have our adhered veneer going continuous multiple floors over our wood stud backing. It can be accommodated with sealant joints. You know, there's any number of things that can be done to accommodate that. The problems come in when it isn't thought of.
Okay. This is a question related to case study 1 and case study 3. This person says that they don't appear to have had a lath. Isn't the lath required by code?
Leah, probably better.
Yeah, I think I've seen a few questions come in about that, and I want to make it clear. Yes, like, there are systems that allow you to use the lath and the scratch coat and the bond coat. You can eliminate that when you're applying the system to a, I think TMS allows a concrete backup, unglazed clay tile, concrete masonry, or cement backer. So both are permitted. It just depends on the backup.
Okay. Do you recommend sounding of adhered units in the field following installation? And if so, how long after installation?
I would say it's probably not a bad idea, but I'd say you get better understanding through just making sure you get a certain amount of sufficient quality control. So ASTM C1242 provides some guidance on that sort of thing. As far as the quality control, removing the units here and there. The sounding can correlate, but it's not a perfect correlation. So sometimes we'll use that more as an investigation tool to see if we can identify the extent of distress. So it may or may not be all that effective.
Okay, we've got time for one more question. What veneer sizes are recommended And in the largest units, as was mentioned being challenging, what is the best installation method / mechanics for applying pressure for these systems to achieve better full veneer bond?
Yeah, so the code limits it, go ahead, I think it was 720 square inches. And I think, but once you get past that 360, you need an installation procedure. And so I think the recommendation is to make sure you're back buttering the units and then potentially having a couple folks, not just one person with the install, to make sure you get that nice mortar squeeze out around the perimeter. And that's where those mock-ups and kind of preliminary procedures are helpful for a good installation. Daren, did you want to add to that?
Sure. So a couple other things. If you've got a shorter dimension, you can trowel in that dimension to allow the air to kind of collapse out the back, maybe even pushing it in and kind of moving it diagonally to get those to collapse and get better contact, using mortars that are especially designed to be a little bit more fluid, and trowels that get you shapes that give you a better approach for collapsing those mortar ridges. So there's a few things you can do.
Okay. Well, thank you again to our three presenters. That was a great discussion, and thank you all for joining us today. We hope it has been educational. So again, thank you so much for your time, and we hope you have a great rest of the day.